In this presentation, we're going to be looking at some common algorithms for searching and sorting in lists of information. It's a very common problem that we have a list of information and we want to search through it and find something. We want to find somebody's name, we want to find somebody's ID, we want to find something that is of a certain price or certain category, and maybe we want to find more than one thing. It's also common to want to sort items. We can sort lists by their prices, by people's ages, and so on. So searching through a list of data and sorting data is a common operation that we want to perform on lists. We'll start off looking at searching, and the most simple search is just what we call a sequential or linear search. In the case of a linked list, you would just traverse over every item in the list until you found something. In the case of an array, you would just search through each index from 0 to the end of the list until you found the appropriate thing. In the past, we've looked at the efficiency of an algorithm in terms of its time. How long does an algorithm take in terms of seconds or milliseconds or something like that? Here we're going to look at a slightly different way. The problem with timing something is that it's hardware dependent. So one processor is going to be faster than another, or one computer architecture is going to be a little faster at something than another. So you can't really compare algorithms like that based on time. So we're going to look at a slightly different way of measuring the complexity of an algorithm, or how long an algorithm might take. One hardware independent way of doing that is looking at something they call algorithmic complexity. And in the case of this search, if we say we have n things, 1, 2, 3, 4, 5, 6, 7, 8, where n is 8 things. So if we say we have 8 things in the list, the worst case scenario for a sequential or linear search is that we would step over all 8 items and it may not be found. So that's the worst case scenario. So we say that a sequential or linear search is going to take n steps, where n is the size of the list of the number of things in the list. So that they say that the efficiency of a sequential or linear search is on the order of n, or they use a capital O with n in parentheses, where n is the size of the list. So they call this big O notation, and it's used to determine what the efficiency or complexity of an algorithm is. And because we're basing it on a math function, in this case n to the first power, or just a constant n, it's hardware dependent. We're not examining how long it's going to take to run on any particular processor. And this is a useful tool in comparing algorithms in different data structures to try to just pick the best one for a particular application. So let's look at a simple linear search, how we might implement one. We just have a blank empty project here with an empty search sort CPP file, and we'll start adding some code here. I'm not sure exactly what I'll need. Vector for sure. Because that's what I'll use to store store some random numbers in a vector. So let's create a list, and it could be a list of anything that we're searching, and we'll keep it simple and make it a list of integers. And we'll put some values in there. So pretty straightforward. And then let's write a search function. Going to pass in the target value that we're searching for. And what are we going to return? And this depends on your application. You may just want to know true or false, whether the thing is in the list or not. In the case of maybe a set, is a value in the set or not. In some cases you might actually want the value back. In some cases you might want to know where it is, because maybe you want to remove it or modify it or something like that. So in the last case, if we want to know where it is, the index of the location that we find something would maybe be returned as an integer. So we can say integer index and do some stuff, and when we find it or not find it, we want to return that index. And something to think about is what happens if the thing we're looking for is not in the list. So what if we search this list for an odd value? It won't be found. What kind of thing do we want to return? We'd like to return some type of indication as to whether, as to the fact that it's not located in the list. One way of doing that is to realize that legal indices start at 0 and count up. So anything less than 0 would not be a legal index, and we could use that as a flag value that indicates that it's not found. So we might initialize index to a -1, indicating that we're assuming we're not going to find it. A linear or sequential search then is just a loop that iterates through all the legal indices. So we go from 0 to, and we need to pass in another item here. We need to pass in the list. For efficiency purposes, we might want to pass it in by reference so we don't make a copy of it, but we also don't want to change it, so we pass in a constant reference. So we have a list, we have a target value, and now we want to iterate through all the legal indices of the list. So that is 0 to size -1, so I less than size. And then at each location in the list, we want to see if the value of that location is equal to the target value. So if list of I is equal to the target value, that means we found it. What do we want to do if we found it? Well, recall that we decided that our search function was going to return the index if it finds it. And so if we found it at lists of I, then the index must be I. So we'll set index equal to I, and if all we care about is finding the first thing in the list, the first thing that matches in the list, then we don't need to search the list anymore, and we can break. If we wanted to find the last occurrence of an item in the list, then we would continue until we reach the end of the list. If we wanted to find all occurrences of the item in the list, then instead of returning a single integer, we might return a vector of integer indices, where each value in the index list would be an index to a matching item in the list. So in this case, maybe we just want to find the first one, or in our application we won't have duplicates, so there'll only be one. We'll just keep it simple as an example here. So now we could ask the user value's position in the list. So we're going to search the list for this particular value that the user entered in and store it in a variable called position. And if position was less than 0, that means it was not found. So we could say that value otherwise, we could say the value is at position in the list. And when we run this, let's just compile this real quick. And we know that we've got the values 2, 4, 6, 8, 10 in the list, so we can test it. And it says to enter in a value. So if we type in a value of 3, it says 3 is not in the list. And if we run it again and look for 8, it says that 8 is at position 3 in the list. And so notice that that position 3 is 0 based because indices in C++ start at 0, so it's going to be 0, 1, 2, 3. So it's actually the 4th item in the list, but the index is 3. So that's a simple, what we call sequential or linear search going through the list. Let's look at the efficiency of a nested loop. Imagine if we created two loops that went from, say, 0 to 10, and then the inner loop went from 0 to 7, and we printed out an asterisk for each iteration of the inner loop. And then at the end of the inner loop, before we started the next outer loop, we would print out a new line. What that would do is print out a rectangular shape of asterisks. In this case, it's going to be 10 high and 7 wide. These loops might be reversed, actually. The inner loop is going from 0 to 7. So these loops are actually reversed. This should be column. I wonder if I can fix that real quick. So I have a slight bug here. Column loop should be the inner loop. So the column loop goes from 0 to 10, so I've got 10 asterisks here, and then I've got 1, 2, 3, 4, 5, 6, 7 rows. So just a slight reverse on the loops, the inner and outer loop. The point is that this is going to print out a rectangular shape of asterisks. What is the algorithmic complexity of this? Well, the real work is being done here in the print, where we're printing out a bunch of asterisks. And how many asterisks are we printing? Because it's a nested loop, the number of asterisks that's going to be printed are the number of times the inner loop executes times the number of times the outer loop executes. So in this case, we're going to get a total, it's the area of the rectangle, we're going to get a total of 70 asterisks. What we say is that because it's roughly n times n, where the number of iterations for each is almost the same. What they do is they say that because it's multiplying together, they say that the algorithmic complexity of this is n squared, because it's width times height units of time. So we say that because it's being multiplied together, they say that in general, the algorithmic complexity is n squared. So what that means is that as n becomes large, the amount of time that it takes to solve this problem or do this work is going to increase exponentially because of the exponent here. And that's generally not a good thing, but in some cases you can't avoid it. You'd like to have an algorithm that's not exponentially complex, but sometimes you can't avoid it. There's nothing really you can do about it. In the previous complexity for a sequential search, we saw that it had a complexity on the order of n, so that's linear, which means the amount of time it's going to take is going to increase linearly as the size of the list increases. Let's look at what we call a binary search. If a list is sorted, and this is an assumption, and sometimes it's common that we have lists of information that are kept sorted. If we have a list that's sorted, and we want to search for a particular value, say the key value that we're searching for is 11, we can maintain 3 pointers or indices into our sorted list or sorted array. We start out with the low being at one end and the high being at the other end, and those are the index values. And then we create a mid value that's just the average of low and highs, be somewhere in the middle. It doesn't have to be exact, but somewhere close to the middle. Then we can ask if the key value is less than the value at mid or greater than the value at mid. And we determine here in the first step that the key value 11 is less than the value of mid. So what that does is it eliminates the top half of the list. So it's essentially like a high-low guessing game where you're thinking of a random value between 0 and 100, and the smart thing to do is to guess 50, and if you're told that it's less than 50 or above 50, then you've eliminated half of the data, and you repeat that by, the next, if it's in the lower half, you'd guess 25, and so on. And so at each step, you're eliminating half of the data until, in this case, the low and the high will cross each other so that the low index will become greater than high, or we find it. If the low becomes greater than high, that means it wasn't found and the indices crossed each other or got inverted. Or potentially we actually find it at a particular location where mid will be equal to the thing that we're looking for. So that's a simple, what we call binary search. We call it binary search because we're dividing the list in half every time. We're looking at one half of the list or the other each time. What is the algorithmic efficiency of a binary search? Well, it turns out that because we're dividing the list in half every time, it's kind of the opposite of raising to the power of 2 or doubling. So that means that this is a logarithmic complexity. It's actually a log base 2 of n, where n is the number of things on the list. So we would say that the algorithmic complexity is on the order of log n. And that's quite a bit better than a exponential complexity. So if you have the ability to use an algorithm that is on the order of log n, that's better than something that might be exponentially complex. Let's look at another one. This is referred to as a bubble sort. And a bubble sort is a fairly simple algorithm, and this is a sorting algorithm where we want to take data that's initially not sorted and sort it. So we've got a list of data here, 1, 2, 3, 4, 5, 6, 7, 8, 9 items, I guess, and we want to sort it. The idea is that we're going to look at the first two locations, and if they're out of order, we want to swap them. So we look at these two locations, and if we're going to do ascending order, then they are out of order, so we swap or exchange them. Now we look at these two locations, the next two down the list, and we ask if they're out of order. And they're not out of order. 54 is less than 93. They're in ascending order, so we ignore that. We go to the next one and ask if these two are out of order. And they are, so we swap them. Now we look at these two, and they are out of order, so we swap them. We look at these two, and they're out of order, so we swap them, and we keep going in that same way. And what ends up happening is that you see that the 93 started out here. At the end of this loop of taking two indices side by side and advancing them through the list, at the end of that, that 93 bubbles up to the one end of the list or the top of the list. And that's why this is referred to as a bubble sort. Now you notice that the list is not completely sorted yet. We still have a 20 that should go further down. We have a 17 that should go further down. So this is referred to as just the first pass of the bubble sort. And we have to make multiple passes. And the maximum number of passes that we would have to make is the size of the list. It turns out we could actually keep a sorted variable. We can make it a little more efficient by asking a question: if we go through all these passes and never make any swaps, then it turns out that the list is sorted, and so we may not have the outer loop go all the way to the size of the list, but that's the maximum that we would have to do, because if you notice, it's possible that an item that needs to go at the beginning of the list only moved one location, so we'd have to go actually n-1 locations. So our algorithm is two nested loops, one that takes two indices and advances them from the beginning to the end of the list, so that's roughly n, and then we know that we have to do this roughly n times to make sure that the list is sorted. So again, that's two nested loops, each of them iterating roughly n times, so it ends up being an n squared complexity, which is not very efficient. It can be rather slow. Let's see if we can implement a bubble sort. You don't really need to return anything for the bubble sort. And we do want to pass in the list, and because we want to change the order of the items in the list, we want to pass it in as a non-constant reference. We want to change the items in the list, change their location, so we pass them in as a non-constant reference. And the outer loop, we said that we need to do a number of passes that's n-1, so this is going to be outer less than list.size and then the inner loop, we need to maintain two indices. So one, we can use the index inner and maybe we could use inner plus 1 as the second one. So remember that we need, on the inner loop, we're going to have two locations. So if this is inner, then this would be inner plus 1, and then the next pass, or the next iteration, this would be inner and inner plus 1. we need to make sure that inner stops before reaching the last thing in the list, or else inner plus 1 will be out of bounds. So we actually need to modify the inner loop to go from 0 to less than size minus 1. So now what we want to do is ask the question, are the two items at inner and inner plus 1 out of order? So if, and you have to decide what the order is, if it's ascending or if it's descending. In this case, they're out of order. For ascending order, they're out of order if the item at inner is greater than the item at inner plus 1. So if the item at inner is greater than the item at inner plus 1, then they are out of order. And in that case, what do we want to do with them? We want to exchange them, and it turns out that there is a swap function that allows us to exchange two items. Allows us to swap or exchange two items. And I'm not sure what header file that's in. It may be coming from the vector. I would assume it's coming from the vector. We can look that up in the documentation if we need to. Well, this example isn't great because it turns out here that the list is already in order. So let me write one other thing where we print out the list. So I'm going to write another function here where we print the list. It's going to be void print or display, and I don't need a target value. I don't need an index. I just need to see out all the items in the list. Put them one on a line, I guess. So then in main, we may want a more interesting data set, one that's not initially sorted to test our sort algorithm. So we may write a loop that puts in random values in the range of 0 to 100. So I'm putting in 10 random values. We can still do our search if we want. I'll just comment it out for now. And let's print the list. Let's print out the sorted list. And I think I might want one more return here at the end of the list. So I've got two functions that I'm really using. One to loop through all the elements in the list and print them out. And then the other one to implement this bubble sort, where we have an inner loop that goes from 0 to 1 less than the size of the list. So it'll go from this location to this location. And at every step on that, every iteration of that inner loop, I'm going to compare the value at inner and the value at inner plus 1. So I'm going to compare these two, and then the next iteration of the loop I'm going to compare these two, and the next iteration compare these two. And at every step, if any of those two sets of values are out of order, so for ascending order is if the first one is greater than the second one, then we say that that's out of order. And now we swap them, and now they're in order. And if we repeat that process for n number of times, 0 to the size of the list, then we're guaranteed that the list will be in ascending order. Here in main, we're putting in 10 random values from 0 to 100 in the list. We're printing out the list in its unsorted original version, and then we're forgetting to call the sort. Let's make sure we call the bubble sort. So there we call the bubble sort, and then we print out the sorted list. Let's see if that builds and runs like we want. So here is our unsorted list, and then here's the sorted list, and you see that it looks to be in ascending order. So that's a simple bubble sort. The bubble sort, as we said, is maybe the least efficient because it's n squared complexity, but it's also fairly simple. It's a fairly easy algorithm to remember. So if the size of your list is not too large, then you can easily remember and implement a bubble sort. It turns out there's a lot of different sorting algorithms, and we'll look at some more of them. And part of your assignment asks you to compare in time some different sort algorithms. One of the last slides here is a comparison of efficiency. Some algorithms, as we said, have different efficiencies, different algorithm complexities than others. Here's a graph of some of these different algorithm complexities. One of the best cases is what they call a constant time algorithm. It takes 1 unit of time. So they say this is a constant time algorithm, order 1. Not many things are like that. I guess if you just put a single value into an array, because you can access the array randomly, as random access capability, then that would be a constant time process, just to put a single value into an array. Log n, an example we looked at was a binary search. Square root of n, I don't know of any algorithms that are square root n, but there could be. Order n is linear, and the linear sequential search is of order n. N squared, so printing out a rectangle of characters or a bubble sort, is n squared. This is n cubed. I don't know of any cubed algorithms off the top of my head. I guess if you had a triply nested loop, there's the potential that it might be n cubed. And then maybe the absolute worst case is n to the n power, where the amount of time goes up dramatically. And I'm not aware of any algorithms that are n to the n. The most common you'll see are constant time, like an insertion into a list, log n, where you divide the work in half at every step, linear, where you don't have a choice, you've got to go through all the items, process through all the items. So say summing up a list is order n because you have to visit each element in the list to add it to the sum. And then n squared if you have to have a nested loop for going through all the items of a list, or maybe a two-dimensional array. Going through a two-dimensional array might be n squared as well. So this presentation we looked at searching through a list and a simple sort of a list, and more, maybe most importantly, the algorithmic complexity in how we can look at, examine, and compare different algorithms in a hardware-independent fashion by saying that their complexity is constant time or order of n or log n. And let me know if you have any questions on this presentation.